Welcome back. In this second part of our AGS introduction, we'll focus on the selection principles that drive the formation of aerobic granular sludge. These principles are key to shaping the microbial community and achieving stable, high-performing granules in wastewater treatment. Let's begin by understanding what selection pressure means in the context of AGS. In AGS systems, selective pressures refer to the environmental and operational conditions that favor microbes with specific traits, especially those that form dense, fast-settling granules. Just like in nature, we can steer microbial evolution in reactors by applying the right selection pressures. This is the foundation of AGS technology. So what kinds of selection pressures are we talking about? There are two main types of selection pressures: microbial and physical. Microbial selection favors slow-growing organisms that store PHA under anaerobic conditions and grow aerobically on that stored energy. Physical selection is based on settling velocity. Granules settle faster than flux, so we retain the granules and remove the flux. These pressures work together to transform flux into granules. Let's take a closer look at how physical selection works in practice. Physical selection is applied every cycle. After aeration stops, granules settle quickly and stay in the reactor, while flux are removed from the top. This consistent removal of flux promotes granule growth and allows for high biomass concentrations, up to 8-12 grams per liter, much higher than in conventional systems. But physical selection alone isn't enough. Anaerobic feeding plays a crucial role too. Anaerobic feeding is another key selective pressure. Volatile fatty acids, VFAs, are taken up without being used for growth, but are stored as PHA. See it as a bacterial fat. This decouples substrate uptake from growth. Only bacteria that store PHA can grow during aeration, which favors granule-forming organisms and stabilizes the system. Let's look at the types of organisms that thrive under these conditions. PAUs, phosphate-accumulating organisms, are the slow growers that thrive under anaerobic feeding. They store both PHA and phosphate and contribute to phosphorus removal. Other slow growers, like nitrifiers, like AOB and NOB, also form compact biofilms. These organisms are ideal for forming stable granules. Now, how does reactor design further support granule formation? Bottom feeding enhances granule formation. Larger granules settle fast and spend more time in contact with infant, allowing them to store more PHA and grow more during aeration. This reinforces granule dominance and ensures VFA penetrate deep into the granule structure. These granules aren't just efficient, they're also highly diverse. Granule hosts diverse microbial communities. Substrate penetration depth determines the active biofilm layer. Different organisms occupy different zones based on oxygen and substrate availability. A single granule can contain over 10 species, each performing unique conversions, making AGS highly efficient. Let's now explore how aeration influences these microbial zones. Aeration creates different redox zones within granules. The outer aerobic layer supports nitrification, while the inner anoxic layer enables denitrification. By adjusting oxygen levels in the bulk liquid, we can steer the aerobic anoxic balance and optimize nutrient removal. Finally, let's see how all these selection pressures come together in the Nereda cycle. The Nereda cycle integrates microbial and physical selection pressures to grow granules. Anaerobic feeding promotes the selection of granule-forming organisms, while settling removes poorly settling sludge, but allows granules to remain in the reactor. Aeration supports nutrient removal. Together, these steps ensure that only stable granules remain, maintaining system performance. This slide shows how granules form in practice. On the left, you see conventional flux, which are small and loose. These flux settle slowly and don't provide the structural stability we need. As selection pressures are applied, these flux start to aggregate and form small granules, shown in the top right, ranging from 0.4 to 1 millimeter. Finally, at the bottom, you see mature granules, which can reach sizes of 0.4 to 4 millimeters. These granules are dense, settle quickly, and allow simultaneous removal of organic matter, nitrogen and phosphorus. This transformation from flocks to granules is the core of AGS technology.